Sound check, mic check, 1 2 1 2. Mic check. Sound check, 1 2 1 2. Right, with a bit of lag, but perhaps acceptable. Testing, testing, testing. 1 2 1 2. Check, check, sound check. Okay, sure. So hello everyone. I am Alexei. I work for an open source program office company called Twig. We are part of a larger consulting organization called Modus. I work specifically with build systems and Bazel in particular, which is what focus on as part of my client work. But there is no prerequisite knowledge on the Bazel itself today, so I'll be giving you a chance to become familiar with the foundational pieces of knowledge necessary to understand how build systems work in general. Some of them apply to Bazel, but again, this is not a requirement. So I'll be spending about 30 to 45 minutes today with you, giving you a very gentle introduction to some of the pieces you might want to know as a software engineer. So Bazel is just an example of a build system. There are a few more, but just to give you an idea how widely used and adopted it is, most of the brands or applications in this list, you can see there, say Spotify is built using Bazel, so the actual binary application that you install on your phone or your desktop device, Kaspersky antivirus software or Tinder app or Google itself, most of its applications are built with Bazel, so say YouTube and even rockets that are shipped to space with SpaceX, some of the software is built using Bazel. So build systems are relevant and are used widely in the industry. Mm-hmm. Sure. Okay. So we can start with just the basic foundation of how the project would look like. So we'll be, as you work on as a software engineer, you would do the development on having the source files, and then something that you operate mostly on. Then you have some third-party libraries that you inevitably will depend on. Then necessary part of the build part is going to be the local dev setup and tooling. So how are you actually going to build software? And this could be, say a dev container that you just open in your Visual Studio Code or your preferred IDE, and that would be it. Or it could be a Docker image that some other part of your engineering organization provides you with, or maybe that's something you have to manage by yourself. And perhaps you have a remote development environment, say Coder, where you have actually cloud-based machines, which you SSH to, and then you use remote development, again, either, say, VS Code or IntelliJ or some other tool. And so that would be part of the build configuration. Apart from the tool in itself necessary, so the environment where the build steps will be done, you would also store the build configuration with the repository. So that would be your, say, linters configuration, your static analysis tools, your testing frameworks and type checkers if it's relevant for your language, and so on. So typical workflow, again, this might be something you're already very closely familiar with. Just to give you, again, reiterate on the foundational pieces, so we're on the same page. You would check out your Git repository, or it could be some other repository. It doesn't have to be, of course, Git, but say version control system. Then you set up your build environment. Again, this could be trivial or could be complicated. Doesn't matter in this particular context. And then you make changes to some sources in your feature branch. Once you're happy, you run some testing, some formatting, maybe some test break. You fix a test, and then test green, and then you would submit and push it to the remote branch, optionally submitting a CI build. So having the source code changes made, obviously this is relevant for a decent size project. If it's a tiny project, then you can just rerun everything, right? And that would be just fine. If it takes a few minutes to run all build steps, then you really don't care about build systems. But for any intermediate or large project, you would care. So you have source code changes, and you say attach a few files. This could be a couple of files, or say 5 or 10 files, which is normally what you would do in a feature branch, unless it's a major refactor. So now you have a choice to make. Do you want to? So what is necessary? You can obviously just skip building anything and just push it to CI. That will be wasteful because it's very likely that you made some changes that you would like to pick up earlier locally, so you can stop wasting resources. Or you could rebuild everything. That's on another side of the spectrum, where you just say, well, I don't care. I just run all the build steps again, just to be sure. And that would work, but again, this could be very slow. So again, your feedback is going to be unreasonable. So intuitively, we understand that we only need to make some changes. We only want to make some build operations. But the tricky part is, how do we find out what we actually need to do? So we had this kind of intuitive understanding, the notion of relevant changes to the context we are in. And perhaps the most trivial and understandable workflow would be just to query your version control system to get the names of the files that you've modified, right? So now that you know you've touched those 3 files or 5 files, you can just run necessary build steps on them. So you know you have to lint on them and format and run tests. Okay, that makes sense. And now we know which files are modified. We also need to know whether we have actually run those build operations on them before. So let's see how this would be done. I use something very trivial example, contrived example, just to not to overcomplicate you with unnecessary details. So what we need to do is just to get something called a SHA, or this is essentially a way to produce a digest of the contents of a particular file. And this is a cryptographic hashing function that, given the inputs as a string of a file, it would produce one large blob, this long string. And this is, when you look at your Git commits and you see SHA, that's the result of a hashing function. So we know we've modified that file, and I would like to get the SHA of the contents of the file, also known as digest. Okay, good. Now that we have the linter, say some abstract tool called codelint, we run our file on that. We run the linter on the file, and it gives us some informational messages saying no errors found, no warnings. Good. Let's save this information somewhere. Obviously, it doesn't have to be a JSON file. I just use it for clarity, because it's very easy to see the content. What we would store as a key value, so we would preserve the name of a file optionally. and then the hash, so the content that is uniquely identifiable for that file, and then also the linter and what we run and the results of it. Okay, good. Now, we just finished running linting. Let's run this linter again on the file, just immediately after. We haven't touched the file, so we haven't modified it, no changes. The SHA would stay the same. Now, if we just rerun the code lint, the question we want to ask the build system, could you check whether you have actually run the linter on that file before for that particular state of the file, that contents? And if so, could you please retrieve this from the cache? And so you don't have to actually run the linting operation. You would just present in the terminal the results of the last successful execution that was run on the file. So that's pretty much it. The caching mechanism is very simple. It's trivial in its concept, but it's very powerful. So what could we cache? Obviously, we could cache the source files with static checking. So anything that's deterministic and simple could be cached. One of the assumptions that I would like to draw your attention to is that this code lint that we run, it has to be deterministic in the sense that it's somewhat a pure function-like. So if you rerun the same file over and over again, it is guaranteed to produce the same output. So it can't use any heuristics or and produce different results every time because we can't reliably cache it, right? So if you have a function that returns, passing two integers, it's guaranteed to produce, say, a sum of those two integers. That is a pure function. And then if you have a function that prints the current daytime stamp, that's a very non-deterministic function because it's guaranteed to produce different results, every moment you run it. So, but we make an assumption that our linter is deterministic in this particular case. It's also possible that some linters are not, so they have to be addressed separately. Maybe some intermediate steps could be cached, and then the parts where heuristics comes in, they can't be cached, and it will rerun every time. Formatting, so you run formatting in a file, you preserve the SHA of the contents of a file, how it was at the time of formatting operation, and then you store the formatted contents as a blob, so that in your key value pair, in this hash map or dictionary, the key would be the SHA of the file, and then the value would be the actual formatted contents of the file. So if I format it once, I revert it back, I run formatting again, there is no need to actually do the formatting, it can just be picked up from the cache. Code generation, your thrift, your protobuf could be also good candidates for caching. Other pieces that are relevant to cache is compilation results, so your C++ shared objects, your Java class compilations. If you, as part of your third-party dependencies, which you download from some online resource, say, if you're a Python project, you download NumPy, which has compiled C code. It has to be compiled for your platform, where you run build on. Once you actually build it once, you don't have to rebuild it every time you again run a test or just run some program, because this could be preserved. So that any build operations done on third-party libraries also could be a good candidates for caching. And if you already use some, if you're a software engineer that operates in different, use different frameworks or tooling, say Docker cache, you already be familiar, C cache for C++, MyPy for Python, and so on. Lots of tools without any build systems, just on its own. Many tools provide caching mechanisms. Interestingly enough, the Go test is actually unique, that it also provides the cache. So if you run in a Go project all tests, and then immediately after you rerun the tests, it is actually smart enough to know that the test results are cached, so you don't have to do that again. And this is unique to Go, and I don't think there is any other programming language that is used in production these days that provides this functionality. So that's all nice and simple. What about testing? So far we only looked at something that's fairly trivial to cache. In order to speak about testing, we have to introduce a new concept called dependency graph. So if you look at this picture, you can see here the diagram that represents the relationships between individual components in your project. This could be source files, could also be just different packages or components. It doesn't really matter. There is some relationship between them. So if we inspect this diagram, we could say that test A, which is here, it depends directly on up A. So your test imports some code from an application because it has to exercise it, so it has to import it and construct something. Then it also depends transitively on libx and comments. So the arrows are pointing to the dependencies. Okay, so we say that up A, libx, and comments are all dependencies of test A. Given this information, we can ask the dependency graph in a reverse fashion. If we made changes in comments, what tests do we need to run? So we would just query it in the reverse way. Who depends on comments? Well, libx depends on comment. Good. Who depends on libx? Up A depends on libx. Who depends on up A? Test A. Okay, there is no one else dependent on test A, so, and we know the nature of this particular node in the graph, so we know test A is a test module, and it's scheduled to run. If we modified secrets, then we know in the graph we can't actually get to test A, because only test B is a node that depends on secrets. Okay, so imagine a large dependency graph with thousands of nodes, using a very simple algorithms such as breadth first search or BFS. You would be able to, or DFS for depth first search, depending on the context, you would be able to identify the nodes that are supposed to be changed or considered to be changed, given arbitrary changes in the graph. So just by following the dependency graph, we are able to know that these particular nodes should be considered modified for, say in your pull request or in your local development build context. Okay, so having this information, how our cache would look like, it's contrived and simplified to keep it reasonable on the screen. There is so much more that could be put in. But if we imagine our cache key, what would be a reliable way to represent everything that is about the cache, the test case? So we would need to have the SHA of the test module itself. Okay, we would need to know all the dependencies SHA, right? So if we look at the dependency graph, we need to preserve the SHA of up A, of libx, and comments, because if any of them change, potentially the behavior of test A might also be different, right? Because it depends on the code defined in those modules. So we need to transitively get all SHAs of all files that are dependencies of test A. Any third-party libraries, so any versions change, of course we want to pin all the third-party libraries versions to specific numbers, so we can reliably put them in a cache. So again, all the libraries, and then transitively, they would also be part of the cache. And once this cache is produced, so we would run the tests, we would store the outputs, so what tests passing, what tests failing potentially, and then all the information about it would be our cache key, and then the value would be the results of a test. So if I rerun the same test again, I don't have to actually run it again, because we know that we haven't modified anything, no changes done. One assumption that is important to emphasize on is the fact that these tests are supposed to be unit tests in a broad sense, that they can't go to some online resources, depend on some state of the system. Because if your test depends on contents of a S3 AWS bucket, then of course it's not very safe to put in a cache, because next moment the bucket might be gone and your test would fail. So they have to be not making any in-network requests or not accessing any file system and so on. So you would normally want to use caching for unit tests. Okay, now as we actually briefly mentioned in some of the aspects of accessing resources and state, an important topic to introduce you to is called explicit versus implicit dependencies. So far in our explicit dependencies, we have looked at the dependency graph, and we know in some build metadata, it's just a plain text file, I can write and say, well, up A is dependency of test A. And that's all good, and build system would be able to traverse the graph and construct this graph behind the scenes in memory. But what about the implicit dependency, something that we perhaps not declared as part of the dependency graph? So any files on the machine that you might have, so you run your test or your compilation command, those files might leak into the build context, and the build system would pick up those files and use them as part of the build. This is a typical works in my machine problem, where it's passing on yours but failing on your colleague's machine. Any system packages you have installed, right? So you have, say Ubuntu machine, and your colleague has Ubuntu machine. You happen to do apt-get install some random package, and now it's your test is failing, but it's passing for everyone else. Environment variables do actually have a chance to impact the test execution, because test might be looking up into environment variables accessible and get the values, and this might have an impact on test execution. Network requests, of course, and then where the build operation takes place. Is it taken in a workspace directory, or is it taken somewhere else? So in some random directory, say home directory versus some temp directory. Again, this might have some file permissions and so on. So to address those problems with implicit dependencies leaking into the build context, we use something called sandboxing. So sandbox is you can think of it as a very lightweight, thin container that is created on a disk in an isolated file directory on a file system that can't have access to any other directories within the file system realm. So you would be passing only declared environment variables in the same way you would use when you run a Docker container, for instance. You pass, I believe it's -e when you want to specify all those environment variables that I do want to propagate in a pass through to the container. In the same way, this is what you would do for the build context as well. The sandbox can't see anything on the rest of the file system. So as I mentioned, this would be an isolated temp directory. So this is similar to what Docker container does. They just, it's a mounted little tiny directory essentially on your disk that doesn't have access to the rest and can't see anything else in contrived explanation. And then again, no networking access. So of course, in Sandbox, you don't want to access some random network resources. Okay, so we talked about those. Okay, that's all good. Now we got a sandbox where we restricted what could leak into the build context and have a negative impact on the caching, of course, but also just on reproducibility, which is something we'll be talking about a bit later. So what are actually true dependencies of the test? Well, we listed all of them, and we know, we depend on source files, we depend on third-party libraries, we depend on environment variables. But we actually also depend on compilers, if that's relevant in the context. Say, for Python, you would be dependent on a Python interpreter version, but if, say, Java, JDK, and C++ for your GCC or Clang compilers. And then any flags you pass to compilers are also a dependency, because you modify some flag that you pass, your copt, whatever, then this would be potentially having an impact, say, your inline optimizations done within the compiler operation that might have a direct impact on the performance of your binary artifact produced. Compilers would go into your system headers just as third-party libraries might go to. So you depend on a curl, and as part of your application library, that depends on libcurl inside, which is a system dependency, and the libcurl might depend on OpenSSL library. And this is something you don't specify in your build metadata, because it would be a nightmare to write down everything that your source code actually depends on transitively. And then in a very peculiar situation, you might perhaps even depend on a Linux kernel version if you do some very low level, say, drivers and interfaces. And then, of course, that would be also have an impact, because in the user space, some things might break between kernel versions, so your source code might behave differently. So I hope I gave you just a taste of complexity of all those implicit dependencies that you kind of have to be aware of as part of the build context. And why it's important, well, if you want to reach, or if you want to get closer to a fully reproducible build. So what does it mean? It means that if I run a build operation now as I check out my repository, and it produces bit by bit a certain content, say binary artifact, I check out the repository later in 1 year, and then I should be able to build the same application, and I should produce bit by bit identical artifacts. They are identical bit by bit. There is absolutely no difference. So that's the holy grail. This is where lots of organizations would like to get, because it gives you, of course, the excellent caching, because you're able to reuse cache effectively. There is no randomness, but also for, say, legal audit and ability to apply backport patches in the future for your previous versions of the software. So now you have a choice. Say we focus on the C++ in simple context. You have to compile the code using a compiler. Now, as part of build systems usually don't provide what we call tool chains or the necessary tooling, say compilers and system headers that they might need and so on. And you have a choice. Do you want to ask a user of a build system to provide this environment? This is what lots of organizations do with, say, Docker build with dev containers, Docker images where this golden Docker image that they've been able to produce, which has everything inside, and you can build, all your build operations happen there. Or you can ask the build system to provide those compilers on your behalf, but you have to be very explicit and specify and declare what exactly you need. Say, I want GCC version 14, Clang version 17, and I want those flags to be used, and so on and so on. So that's tricky, but that's what we ideally want to do. So then, of course, if you specify it per, say, component in your large organization, then different teams, they can use different compiler versions and flags when they compile their own application. They are not tied to a single Docker image. Whenever you make some changes there, then everything should be considered change, right? Because it's very hard to know what is actually should be considered modified when you make changes in a large dependency like this. So from a very trivial way to provide this environment, I already mentioned earlier, that would be your way, say you have shell scripts or a bunch of readmes, where a new developer comes in the organization, then they would be able to set things up for them. That's difficult to arrange and error-prone. Perhaps a better approach, then you have this golden Docker image, which has everything, or multiple per component, say. It does save you the time and effort to make sure everything works on your machine. And then ideally, again, that should be build systems provided in the sense that you declare dependencies on your compilers, and then say you will download them from GitHub or some other binary repository manager. And then you need to specify the SHA of the compiler that you download, its version, all the flags. They should be all declared in plain text as part of your build operation. So that then your build would be reproducible, that you could rerun many times and it would use exactly the same configuration, exactly the same setting. This is hard to arrange in practice, but you can still get closer to, the more you declare instead of relying implicitly, the better your will be in long term. Two other topics or terms I have to introduce you to when talking about build systems, and something called a full and incremental or partial build. You can think of a full build, say you got a new laptop, you set it up, you check out your repository, and you build your project as the first thing. That's something you would do, right? So that's a full build, also known as cold build, when you just have to run everything. There is no cache to reuse. There's nothing there. And this might take hours. An incremental partial build, this is where you have an existing repository which you already run full build on, and you made some changes there, a few files modified, and now you just want to do the absolutely minimal changes necessary to confirm the project still builds and all tests are passing. And this is where you would be targeting seconds or minutes to have this feedback loop very short, so you can iterate quickly. But what about full builds? Okay, for partial builds, we got it. We use a dependency graph, we traverse it, we identify files that are modified, and then we see what kind of build steps are necessary to run them. If we mark the node in the build metadata as test, okay, we need to run tests on them. If they are sources, okay, we need to run linting and formatting. That makes sense. And we can do, pretty good on that. What about full builds? You clone the repository locally, you build everything, say master branch, main branch. Intuitively you understand, well, this might be already built in a CI, right? So when you push the master, your merge request, pull request is merged, master build triggers in, and those compilation steps, they have actually been done already in some CI machine, right? So what if we could take advantage of that? Well, this is where we introduce the concept of a shared cache or remote cache, right? So what if the CI agent that has been built in your master branch, what if it stores that cache information somewhere, and the agents can write to the cache, but then you developers, you would be able to read from the cache. So whenever you check out your master branch locally, before actually starting doing the build system would be checking, hey, let me look into the shared cache that we use within our organization and see if someone has built those sources for this SHA as the contents that you have now. And oh yeah, I see that actually this has been built a while ago, so let me pick it up for you. In this way you can drastically improve the performance of your builds because you can rely on the remote cache. In peculiar situations you might see, I don't think it's very, it's quite rare, but I do think it's worth mentioning that you could consider also letting developers write to remote cache. Obviously, it has a certain implications that if something goes wrong with some local development, then they would be able to write to cache something that's not actually correct. And then other developers would be impacted because they would be pulling things from cache. And this is called cache poisoning, a bit of advanced concept, but it's still possible. So a useful case would be, say, you work in a feature branch, you run your test, you compile, you waited for 1 hour, it's all green and happy. Now you push it to a remote branch. And then, of course, the CI agent is not aware of anything that you've made locally, but it's been 1 hour of build operations. So they might actually benefit from having this information readily available. So in this way, of course, it does feel nice to be able to have this cache readily available. What about testing? Can we do better? So for local builds, okay, we figure out we got the shared cache, and that's essentially it. So in a large organization, using build systems such as Bazel, it's impossible to maintain adequate speed without caching, and remote caching in particular. So that's a pretty much de facto standard that you have to operate with. What about testing? So for local tests, you are limited by a number of CPU cores that you have, right? So say you have a test module with, let's say, 16 test cases, just exactly how many cores you have on your machine. So you can run, distribute each test case would be run on each core. And then if your slowest test case is, say, 1 minute, then your testing time would be 1 minute. If you have 100 test cases with one the slowest is 10 minutes and the rest is just 1 second, you still have to wait for 10 minutes. This is one of the incentives why you would want to split a large test case into smaller ones that are faster to operate, because you can parallelize more aggressively. So intuitively understand, well, I just need more CPU cores. So one way is to get a beefier machine or use other machines. So you can SSH into some remote server and run tests there. Again, you're limited by hundreds of cores, whatever you would be having accessible there. And then so you would just have multiple machines. And you don't want to do it by yourself, doing all those crazy SSH connections. What you want instead is to have build system doing those operations. So you ask your build system, hey, could you please use the dependency graph, because I've declared all the dependencies manually or semi-automatically for my components. Now I made some changes. Go and figure what test modules should be considered modified, because reversively they go back and dependencies propagate down to those tests. And now distribute them across whatever machines that you have accessible right now that you can start. So the build system with some orchestration tooling would be able to start hundreds of machines, thousands if necessary, distribute all the test cases, run them, and then kill them and shut down immediately once your test cases are completed. So this is where you would be able, in a cluster agent, ideally you might be, if you work in a feature branch, you pushed a CI remote build, it's done something there, and then it's, oh, it's actually the test is broken. Okay, you go back to your machine, you made the fixes, and then you push it up again. Of course, you do want to use, take advantage of the cache that you have already built on that particular agent, which is specific to your branch. It's not relevant for anyone else. So the agents, if you start with a new machine every time, then intuitively you understand that, well, that will be wasteful, because a new agent will not have any prior knowledge of what you've built. So what you want to end up is on the same machine somehow, or using the same shared cache accessible for your branch. A bit of a peculiar topic, I guess, but something that's very relevant for large organizations. Okay, so this is pretty much it. What I want to give you in a reasonable amount of time, just enough to get a taste of the build systems, what kind of problems they solve, and some of the interesting approaches that you have to take in order to be productive using them. If that sparks interest, what I want to give you is kind of 2 tracks you can explore. Of course, you can combine them. So one is build engineering, and one for SRE, DevOps, IT, system administration, networking style. So in one path where you would like, if you would like to learn more about build systems and some of the more advanced topics, feel free to look up a branch of mathematics called graph theory, which is very relevant for dependency graph management, as it gives you a bunch of interesting applications for being able to improve the structure of dependency graph, its shape, dependencies. Just an example, say everyone is modifying in arbitrary pull request, they touched a few files, and now all of a sudden all tests have to be run. So in dependency, everything is so interconnected that just everything is considered changed on every commit. that's going to be counterproductive to your development cycle. So if you're smart about dependency graph management, then what you can do is to identify those critical connections between components and break them to, say, refactor and move some of the code members aside so they're not in the same component. And you can save hours, or half an hour, or minutes, whatever your context is on the graph. And so they save in developers' time and also CI time, ultimately money, because either you run it in the cloud or on premises. Caching optimizations. That's also interesting problem that you might be interested in looking into. So imagine you compile Java on Mac, Windows, and Linux, and you have developers using their own preferred devices. Now they produce a jar, compile Java, which JDK provides guarantees for. It should behave in the same way unless you use some platform-specific calls. But let's just simplify it and say, well, it's guaranteed to behave the same. But the jar files, they might be different bit by bit, and likely will be, because metadata is still associated, perhaps inside them. So how would we cache it? If I built my application and it took me 1 hour to build, it would be wasteful not to let developer on Mac or Linux to take advantage of that. So some kind of smart caching mechanisms where we maybe need to patch those files before putting in cache or something like that and then restore them somehow. That's an interesting problem to look into. Hermeticity and reproducible builds. So that's the whole story, the whole movement behind reproducible builds. You can look up online, again, for sensitive industries such as automotive or biotech. You do want to be able to rebuild your commits knowing that there is nothing else that leaks into them, and all the information is declared fully, and they could be rebuilt safely in the future. And then on the DevOps infrastructure part, so something you might be interested in is looking into, say, telemetry or metrics collection. Cache and hit rates is very common to track because, say, in all our build operations, all the linting, formatting, testing, everything that we need to do, we've been seeing 90% of the operations, they've been picked up from the cache, which is great because it means we can save a lot of time just reusing what has already been done. And then after a few pull requests, all of a sudden it drops to 70. So if you set up your alerts and then someone on call, or you just regularly look up and review those cache hit rates, say weekly or monthly, you would be able to see, oh, that something is degrading, and what could be the reason? Well, some changes in dependency graph, perhaps, or something is leaking into some detail that is specific to the build environment is leaking into the build, and then it's worsening our cache hit because it's going to be every time the same. Every time it's going to be a new value to be put in the cache. Testing strategy, if you're into machine learning or LLMs or in whatever capacity, flakiness detection is very interesting because given those results of a test execution that you run, how would you know if the test is flaky? How likely is it to be flaky? So you would need to store the information on the previous executions and then see, well, those developers, they touch those files. The files are actually irrelevant to the test, but the test failed on n times in that time frame. So it's likely more to be flaky, and then you can schedule it or mark it automatically or run it in better isolation or automatically run them 10,000 times in a nightly job just to confirm whether it's true or not and exercise it harder. So those are interesting problems you would be looking into. Remote execution, so if you're into Kubernetes or anything similar in the orchestration sense, then that would be also a good example. Again, back to our test parallelization, you got hundreds, thousands of tests. How would you efficiently parallelize them? How would you pick up a right machine type on types of cores and memory needed? Again, some heuristics and machine learning plus some smart management of those resources. What is the least optimal size of the machines that we need that would still get the job done, but we don't have to pay too much for the cloud environments either. Cloud engineering, that's an excellent opportunity. In a large organization, if you do, you spend thousands of hours every day on build, if you're able to use, say, spot instances, which is a special type of instance the cloud provider might kill whenever you use it, but you pay a lot less money for them, just because another client is actually ready to pay more, so they would be using that for them instead, so you would be just left with a dead machine. That's part of the terms and conditions. But if you only need a machine for 5 seconds or half a minute to do the test case, that could be an interesting idea to try to run it on spot instances, and then if they kill, that's fine. Your orchestration tool would just rerun test case again on a new spot instance, and you might be saving a lot of money. So that would be interesting optimization to look into. Okay, so if you want to learn more about build systems, of course, the major build system known that I already talked about before briefly is Bazel. It's originally developed in Google, open sourced a while ago. If you're looking into reproducible builds, so you would like to make sure it's bit by bit identical, so that's a fun exercise to try at least, learn more. So you go to bazel.build, and then for reproducible builds, it's reproducible-builds.org. And graph theory, I just have to call it out again. I find it to be very interesting, has lots of useful applications to the dependency management. You can learn more about the Twig and consulting services that we provide, the twig.io. If you're looking into learning more and more about me and some of the open source work I do, you can learn more about me on the website of mine, alex-tereshenkov.github.io. So feel free to reach out as well. And thank you.
I have a question for you.
Sure, go ahead.
You talk a lot about the build system and we have different build systems like I don't know, maybe Gradle and also the Bazel, whatever.
Right.